Hello everyone, my name is Alfonso Amat. I am CEO and co-founder at CellRep. At CellRep, we rejuvenate cells without gene editing. We see cells as nature's supercomputers, and we see aging as a software problem. And we are starting to debug it. So today we'll try to show you how a frog, a sheep, a samurai, and Markov chains are helping CellRep to start to improve cancer treatments and to get closer to the longevity escape velocity. So what we see here is Markov. I guess all of us have seen it. This is a typical transition. In finance, it's called a stage transition. In biology, it's called differentiation. What you see here, for example, an arrow, the probability of going back. Okay, so keep this in mind for the continue. In 1962, we have John Gordon that was able to clone a tadpole from a mature cell of a frog. Decades later, the same thing was proved with Dolly. What's the deep insight here? They were cloning animals with mature cells. So the deep insight is the DNA is intact, okay? So through time, still the DNA is intact. So then you have Shamanaka, this guy with the name of a samurai, that with his 4 factors, he was able to get a cell from, for example, a T cell, almost any cell, back to a stem cell. The magic here is he is able, for example, mitochondria go back to their primitive state. Telomeres grow back. I remember when I was young and people said, telomeres always shrink, so it's impossible to rejuvenate. Wait, telomeres grow back, and all the epigenetic information is deleted. So we all know the cancer risks, yes, but there's a catch that for this type of things is really dangerous, is that the cells forget their identity. Forgetting the identity means that, well, in a nutshell, you don't want your neurons to forget their neurons, correct? Finally, we have David Sinclair. David Sinclair, yesterday people talked about him. I'm a fan of David Sinclair. He introduced the information theory of aging, and he showed that aging, in a nutshell, is information loss. So if you think when any cell in your body has the same DNA, but the DNA is twisted and changed with epigenetic flags, okay? So for example, once a neuron is a neuron, there are a lot of flags that say, I am a neuron. But through time, these flags get corrupted. They move from one place to the other, or new flags are turned on and on. So in a very colloquial way, we can say that a neuron start getting confused, and it's a little bit a neuron and it's something else. So he was able to identify this, and what we see is that many people are talking about fixing disease with gene editing, correct? So this is like hitting, I'm an electronic engineer, and this is like trying to solve a software problem hitting with an ice pick in the middle of the motherboard. You don't want to do that, because what has we seen with DNA, what was proved by Shamanaka, what was proved by John Gordon, that the DNA, the hardware is okay. So we need to fix the software. So that's where our insight comes. Our insight says we need to move back through the Markov chain, but slightly, partially, move back, and then when you do that, with small molecules, you allow the cell to self-heal. This started with Federico Perdomo. Sorry, he's co-founder also. He was working in France, and he was working in HIV elite controllers. HIV elite controllers are very special elite individuals that when they have HIV, they control it without treatment. And he said, why is this? Why elite controllers do not get the disease? Well, they get it, but it doesn't grow. Why? He identified the immune system. This is the differentiation process within a T cell. T cells are our soldiers that are in our immune system that fight against diseases. Okay, so if you see, actually, in the elite controllers, they are moved to the less differentiated. Less differentiated means that they are more robust, they have more killing capacity, okay, and they reproduce better. And he started to think, am I able to do exactly that in any patient? Can I get any of you and get a small molecule and take you back? And he was able to. He was able to change the transition back and improve it in a way that you could get with small molecules the ability to move back in the system. So we decided to start a company on the shoulders of Federico's discovery. The shoulders are that we said we are going to combine AI to identify the targets. So this is how the cell works to understand how to move back. Then we have the in vitro team that will validate in silico. In silico creates a lot of mistakes. That's brilliant. It gives you the guide, but then you test it in vitro, and if it works, then you take it in vivo. The interesting thing of this model is that it goes back and moves. This we'll see in these days that several people are already doing this type of things with small molecules. Like EMBO Journal just published that with a combination of 2 small molecules, they were able to reprogram a cell. So how we do this? We have 8 models, 8 machine learning and diffusion models that help us to identify first within the cells what are the difference between the more differentiated, the less differentiated, and then we find small molecules that will bind with several targets. What these small molecules help us to do is the artificial intelligence will help us to do is small molecules, we know that they have multiple targets. Because they're simple and small, they will target in many places. The model also helps us, the diffusion model also helps us to understand how to bind where we want and how not to bind where we don't want. This is one of our results. This is a 97% movement back in the Markov movement, in the Markov chain. And here we see a 3-fold increase in younger cells. You might wonder, yeah, Alfonso, and so what? We are here. Okay, let me show you Baylor College of Medicine. This is in the US, this is a CAR-T used for breast cancer. For those that doesn't know what is CAR-T, CAR-T is using your immune system to fight your disease. So cells are removed, they are trained, they're expanded, and taken back to the patient. Okay, so this is to fight breast cancer. So this is the CAR-Ts from Baylor fighting cancer, breast cancer, and this is with our compound. You see that when the cells are less differentiated, suddenly they kill twice. What else? This can be applied also in HIV, in hepatitis. I already explained that, no? So when I was trying to explain here the size of the market, I was saying, well, longevity is $1 trillion market. HIV, billions. Hepatitis, billions. Okay, so let's just take CAR-T just to have an idea. So last year generated $7 billion, and it's projected to grow to 30 billions for the most conservative and 188 for the Polaris. Whatever, even if you take the conservative, it's a massive opportunity by selling products that improve your immune system, okay? So if you see competitors mainly, you will have 2 metrics to look at, two variables. How flexible is the solution, and how scalable is the solution? So we already talked what happened with DNA, no? With DNA, gene editing, boom, you're breaking the solution, it's permanent change. Then you have RNA. RNA is outstanding, it's really working, but the problem is that it's extremely difficult to deliver and extremely difficult to combine. Small molecules bring exactly the both things, so it's easy to combine, extremely safe, so you can do this. So let me tell you a challenge that mostly people ask me, but isn't it, you're using small molecules, what will happen, for example, in the patent battle? Yes, it's a landmine. Okay, so it's extremely difficult patents. So what we do, we use, again, our AI model that helps us to show us path to move in the Markov chain. We start finding and testing the small molecules. We start going through the patent, through the legal issues from patents and all that, and then we find the ones that will work. So we executed so far with less than $500,000. We have identified 5 small molecules already approved by the FDA, 35 compounds generic, 15 targets to move back with a simple team. So we are just 10 today, 50% of the team in Colombia, 50% in Argentina. We have Federico already talked about him. He's an expert on lymphocytes. Manuel Franco, his decades of experience in vivo experiments. Julian, decades in AI. And myself, I already had an exit to a company that's listed in New York Stock Exchange. And previous to that, I worked at Amazon, leading Latin America. So we are advised by the best. Because of the time, I'm just going to talk about Luca Gattinoni. He's the guy that identified how the cells move and how this can be used in cancer. So he'll help us here. So as I mentioned, we executed with less than $500,000, and now we're raising 4. Because with 4, we know that we can complete the entire immune system. And then, once we finish that, because the way it works, our flywheel, the way we learn, we can take all this knowledge to start working on neurons, pancreatic cells. So we are learning how to rejuvenate, and we're improving that. So yes, the massive market, the technology is working, AI-guided advantage with FDA-approved tools, and we have the right team to execute. So I hope I was able to show you that a frog, a sheep, a samurai, and Markov chains help us. So this is a message that I would like to leave here with you. Longevity escape velocity requires hundreds of breakthroughs. We are taking one of them, that is teaching cells to become young and learn to bring that value back to the entire body. Thank you very much.